Hello, everyone. Let me begin today's session with a question. Have you ever wondered why a diamond is so rigid that it can cut through glass, while a simple piece of plastic bends so easily? The secret lies in the fascinating world of solids. As you already know, matter exists in three states: solid, liquid, and gaseous. But solids stand apart because their particles, whether atoms, ions, or molecules, are packed so closely that they hardly move. This tight arrangement gives solids their definite shape, high density, and incompressibility. We broadly classify them into crystalline solids, which have long range order, and amorphous solids, which have only short range order. For example, ice and sodium chloride are crystalline, while glass and plastics are amorphous. Let's dive deeper into what makes these two categories so different.
Now, let's take a closer look at crystalline solids. Imagine arranging rows of chairs in a perfectly repeating grid for a school assembly. That's exactly how particles are arranged in a crystalline lattice. These solids have a definite geometrical shape and a sharp melting point because the entire structure breaks down at once when sufficient heat is supplied. One remarkable feature of crystalline solids is anisotropy. Their properties, such as refractive index and electrical conductivity, change depending on the direction in which they are measured. Cut a sodium chloride crystal, and you will notice it cleaves neatly along flat surfaces, producing smooth, clean edges. Famous examples of crystalline solids include sodium chloride, diamond, quartz, and metals like copper. They are nature's perfect architects, showcasing beauty in order and symmetry. Now contrast this with amorphous solids. Picture a jar filled with marbles shaken randomly. There's no repeating pattern, just a short-range order. That's how particles are packed inside glass, plastics, and rubber. Amorphous solids do not melt sharply. Instead, they soften gradually over a range of temperatures, which is why glass blowers can mold glass into beautiful shapes. Unlike crystalline solids, amorphous solids are isotropic, meaning their properties, such as conductivity or optical behavior, remain the same in all directions. And when broken, they don't split cleanly, but rather produce irregular, curved fragments. Everyday objects like window glass, rubber bands, and plastic bottles are excellent examples of amorphous solids. These are often called supercooled liquids because their structures resemble that of a frozen liquid. It's now time to compare crystalline and amorphous solids side by side. Crystalline solids melt sharply at a single temperature, whereas amorphous solids soften gradually. Crystalline materials are anisotropic, meaning their properties depend on direction, while amorphous solids are isotropic, showing the same properties everywhere. Similarly, crystals have definite heats of fusion, while amorphous solids do not. And most importantly, crystals exhibit long-range order, whereas amorphous solids possess only short-range order. For this reason, we sometimes call amorphous solids pseudosolids or supercooled liquids. Now let's look at their applications, which make them vital in both everyday life and advanced technology. Glass is the most versatile amorphous solid used in windows, bottles, lenses, and laboratory apparatus. Rubber is another example, used in tires, footwear, conveyor belts, and hoses. Plastics, which are also amorphous, are everywhere in our daily lives, packaging, containers, and furniture. One of the most exciting applications is amorphous silicon. It is used in solar panels to convert sunlight into electricity. Isn't it amazing how the irregular structure of a material like amorphous silicon is helping us move towards renewable energy? Here's something even more fascinating: the concept of glass transition temperature, or TG. Amorphous solids do not melt sharply like crystals. Instead, as they are heated, they pass through a range of temperatures where they gradually soften. This range is called the glass transition region. Below Tg, they behave like rigid solids. Above Tg, they become rubbery or viscous. This concept is extremely important in polymers, where flexibility or hardness depends directly on Tg. For instance, plastics used for bottles need to have a higher Tg to stay firm, while plastics used for packaging films need a lower Tg so they remain flexible. The science of controlling Tg is crucial in polymer engineering. Let's quickly revise what we've learned today about amorphous solids. They are solids without long-range order, often described as supercooled liquids. They are isotropic, soften over a range of temperatures, and break with irregular cleavage. Their density and heat of fusion are lower than crystalline solids, and they can transform into crystalline forms over time. We also saw everyday examples like glass, plastics, and rubber, along with advanced uses such as amorphous silicon in solar panels. And finally, we explored the glass transition temperature, a property that makes polymers and plastics so versatile in industry. So, I hope now you see that amorphous solids are not just textbook concepts but materials shaping modern life, from the windows in your home to the solar panels powering renewable energy. Chemistry is truly the science that connects structure with application. I'll see you in the next session with more fascinating insights into the world of solids.